Good morning and welcome to Emergence and Phase Transitions, Week 2, Lecture 4. Today we're going to be talking about spontaneous symmetry breaking. We're going to talk about the term ergodicity breaking, and we're going to understand how it is possible that that one can have long-range order, that one can have spontaneous magnetization in the first place. Now, we will also start the theory of how to do mean field theory in a more systematic way for the Ising model. Now, just a couple of quick announcements. Homework 1 is now available to you. It was sent out by email yesterday. The due date has been extended from what I had legacy in the Canvas system. I've reduced the number of questions. One is mandatory, and choose one of the other ones that you feel interested in. And that's all you have to do to get full credit. Those of you who want complete mastery of the topic, if you have time, I encourage you to try all of them, either now or at some later date. And I also want to mention that I've added a new problem to the homework assignment, one that is based on the 10-second theory of the ferromagnetic transition that we talked about in the beginning lectures. Now, last time, the highlight of the lecture was that we proved that emergence is actually impossible, that there are no phase transitions at any temperature. And roughly speaking, this is how we did it. So look at the panel on the right. What we were doing was we wrote down the Ising model in an external magnetic field, and we noticed that it has a particular symmetry. If I change the sign of all the spins, I flip the spins from +1 to -1 or from -1 to +1, and I simultaneously change the sign of the magnetic field, the external magnetic field H, then I just get back the original Hamiltonian that I started with. So this is a symmetry of this Hamiltonian. We call it time reversal symmetry, Z2 symmetry, up-down symmetry, spin flip symmetry, whatever you want. Um, what this implies is that the magnetization, excuse me, as a function of H is simply an odd function. And because of that, when we're interested in spontaneous magnetization, in other words, what happens when the external field is set to zero, and we're trying to understand how it is possible for spontaneous magnetization to occur, that means we set H equals 0 in that, and that tells us that M of H equals 0 is always equal to 0 for any temperature. This is an identity. It's an exact result, so there is seemingly no emergence. We also showed that non-analyticity can only arise in the thermodynamic limit as n goes to infinity, and we looked at the bulk free energy per spin as a function of external magnetic field. And what we saw was that for n is less than infinity, it is a perfectly analytic function, but the only way that we can get something non-analytic is if it develops a non-analyticity. In this particular case, it turns out that it develops a cusp, as you can see shown in the picture on the right. And so the form of the free energy per unit spin has the form shown. And indeed, because of that cusp, actually in the limit as h goes to 0, there is still a non-zero magnetization that is possible, either a positive one or a negative one, depending on what happens when you take the limit as h goes to 0. In the figure at the bottom, you can see the magnetization plotted as a function of h. And as h goes to 0 for n being finite, you can see that it always goes through 0, just as our theorem predicted. But what apparently happens, and I haven't yet proved this to you, but what apparently happens is that for n equals infinity, as I take the limit as h goes to 0 from the positive side, m goes to 0, m does not go to 0 as h tends to 0, but goes to a non-zero value, which I'm calling ms. And if I approach from the negative side, h going to 0 from below, then m tends to a value which is minus s. And ms is a minus ms because of the underlying symmetry of the Hamiltonian. So when you hear the term spontaneous symmetry breaking, this is what we really mean. This is exactly what spontaneous symmetry breaking is. So to answer the question, what is spontaneous symmetry breaking? So it is not that in zero field, M suddenly acquires a non-zero expectation value. So that's really, I mean, that's how you hear about it. So that's what people often talk. But you can see that it's not really quite correct. It can't be correct because rigorously M has to be zero. So what we really mean is that we apply an external field, then uh, take the limit h goes to zero from plus or minus side, either you like, and for t greater than zero, m s is equal to zero, and for for t greater than tc, I should say, sorry, and for t less than tc, then apparently the limit of m of h uh, 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 equals, as I take the limit, h goes to zero, plus or minus is plus or minus m sub s. So that's the phenomenon, and now we're going to try to understand how this is even possible. So to answer that, we need to understand how it is possible at all for there to be a phase transition. And so we're going to have to go back to the foundations of statistical mechanics, and that means we need to talk about ergodicity. So what is ergodicity? Well, in statistical mechanics, we have this notion that if we have, say, some dynamical system that is exploring its phase space, so this is not the physical space, this is phase space that I'm drawing over here, and a phase space uh, is basically just let's suppose I'm talking about a bunch of particles bouncing around in a box. The particles have position qi and that varies as a function of t. They have momenta pi as a function of t, and then I have the set uh, of momenta and positions as a function for each particle I equals 1 to n. And these quantities, let's say I'm in 3 dimensions, then there would be 6n quantities here. So this is a 6n dimensional space, and what that means is that if I take a point in this space, a point in this space, that represents the state of the system. Now, when I use statistical mechanics, what I want to compute is some variable. So let's suppose we are interested in some variable f. Some variable that depends on the state of the system. And what I want to know is its expectation value. What is its average value? For example, I might be interested in higher moment. I might be interested in its probability distribution. But for now, let's just talk about the average value. then what the ergodicity tells us, which is an assumption, but can be demonstrated in a more technical way, is that what I want to know is this: if I track this variable f of t, and this variable depends on the full phase space of the system. So I'll just denote it like that. The system is traveling around in phase space. I'm going to measure this at some time, average over all times from naught up to say some T max. It's a time, not a temperature. Divide by T max, and then take the limit as T max goes to infinity. So this is the average value of this variable f, and and this is a dynamical average, and the ergodic theorem tells us that we replace this ergodic, this dynamical average with a phase space average. So I'll write it down, and I'm going to say a bit more about it in a minute. So by a phase space average, what I mean is I take a thermal expectation value of f, now written down as a function of q and p, and I'm going to multiply that by the Boltzmann factor, e to the minus beta h, take the trace, the expectation value, normalized by the partition function. And this is then the average of f over phase space. And so because we're taking the long time limit here, that means that why do we take the long time limit? This long time limit means that we are in thermal equilibrium at long times. And that's why we do that. So let's go back to our phase space. So here is our starting position, and now what happens is we run time forward, and so what happens is the system creates some trajectory that presumably fills all of phase space and eventually goes arbitrarily close to every point in phase space like that. So that's the idea. And then what the Boltzmann distribution is supposed to be is it says instead of taking a long time average as I go through this trajectory, all I simply do is I take a region of the phase space. I look at the density of trajectories in that region, and the density of trajectories in that region is the Boltzmann distribution. And so that tells us then, so if this is really true, if it is really true that the system is ergodic, then we can replace the long time average with this phase space average. So this is an assumption. The word ergodicity means wandering. And so the system is just meandering through phase space according to Hamilton's equations of motion, and you get this picture here. So what this is telling us then is that the probability of each point in phase space. I'm simplifying here, but let me just say it like this: the probability density of each point in phase space So that probability density then is given by e to the minus beta times the Hamiltonian divided by the partition function. And so the Boltzmann distribution is just the density of these trajectories. Now, what we did last time was we showed that if m is equal to 0, we showed that that was true, and this makes sense because for every state in the system, has a time-reversed state with the spin flipped. Okay, so think about it like this. Um, we're averaging over all the states. We could over here, let me put it do it over here since you're probably watching on this side. If I were to draw a line through this phase space, think of this now as the phase space for a magnet, not a bunch of particles. This might be the states where m is greater than 0. These are the states where m is less than 0. And for every state in m greater than 0, there's another state with m less than 0. So when I do the average, I'm going to include every state and its opposite state. And so that's why the magnetization is equal to 0. So every state is a time-reversed state with the spin flipped. So that means that when we average, then that means we're going to get 0. Okay, so that's what's happening. So the conclusion from that simple argument is that the Boltzmann distribution is wrong. Well, so it's not correct, at least for t less than tc. And so we have to understand that in a little bit more detail. So let's go and do that, and that's what we're going to be doing with ergodicity braking. So let's go back to our picture then of our phase space for our magnetic system. And we're going to look at this phase space for the case where H is equal to 0. So we're not interested in having an external magnetic field, at least for now. We're going to order these states in this sort of cartoon picture so that these are the states with m greater than 0, and these are the states with m less than 0. And the only way that we can have a non-zero value for the for the magnetization is if there's ergodicity braking, namely that we start at some point over here, and then instead of going through the whole phase space, we only go to the states where where m is greater than 0. And so the basic idea is um, that we avoid this disaster by actually restricting the states to be the ones where m is greater than 0. Well, of course, there's nothing special about m being greater than 0, so I could equally well have drawn this picture like this. M is greater than 0, m is less than 0, and then if I'd happened to start with a state where the magnetization was negative, I look at my trajectory and it would be doing something like this. And so this is what I mean. This is the sort of phase space picture of ergodicity braking. Excuse me, phase space picture of ergodicity braking. And if you have this, then the cancellation that we had before, how do I spell cancellation? Well, something not like that. How about this? Cancellation of states is avoided, and so that's the basic idea of ergodicity breaking. We've broken ergodicity because now the system is ergodic in a restricted region of phase space. So, the basic claim then is that the following is true. I haven't proven this to you yet. I haven't even said why it happens. I've just told you that if we can show that this is true, then it will answer our paradox of how emergence actually happens. So here is the idea. So for temperatures greater than Tc, then what we claim is that the probability of observing the system in equilibrium in some configuration specified by the spins, that is equal to 1 over the partition function e to the minus beta h as a function of all the spins. And so the system is fully ergodic. And then to contrast that, when T is less than Tc, then what we're saying is that the probability of equilibrium of observing the system in a specified state, P of Si, that is equal to um, 1 over the partition function, say, taken over the positive region of phase space. I'll call that Z plus, e to the minus beta h. And then we throw away, so I've got a Heaviside function here, all the states where the sum over I of Si is negative. So this is a Heaviside function that is 1 when its argument is greater than 0. I'll write it down in a minute. So I can either have that, or I can have P equilibrium of S is 1 over the restricted partition function over the lower part of phase space, e to the minus beta h times the Heaviside function of minus Si. And I mean by the Heaviside function, theta of x is equal to 1 if x is greater than 0 and 0 otherwise. So that's this will satisfy our conditions. Well, I say 0 otherwise. I really mean x is less than 0, and how it's defined at x equals 0 is a tricky issue. We don't really need to get into that. But that's the basic idea, that somehow the system is now ergodic only over a restricted region of a phase space. So we can think of this as being a state that is partially ergodic. Okay, so 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 that's the idea. So the summary, and I'm going to show you where this comes from in a minute. So the summary of this idea is that you have the Boltzmann distribution either in m greater than 0 region, or the m less than 0 region, and p is equal to 0 if the system magnetization is not positive or negative, respectively. Okay, so what that means then is that essentially I've got two probability distributions and not one. So you can think of it as something like this conceptual picture here. Um, Before we have our regions of phase space, and so I could either have p is non-zero here, but p is equal to zero here, or p is equal to zero here, and p is non-zero here, and this is the idea then of ergodicity breaking. Okay, so that sounds great, and I would certainly answer the problem, but now we have the question of how does ergodicity breaking even occur? And and the basic idea is what we're going to do is we're going to compare. Well, not really compare, and I don't really mean compare. I mean compute. So let me write down compute. We're going to compute how long it takes. And I'm going to it takes for a system with m greater than 0 to uh, to go into the region where m is less than 0. And I'm going to do that in the limit where h is equal to 0. And I'm going to call that time, call this ergodicity time. Let's call this t. And I'm going to, and in particular, an important part of this argument is we're going to compute this for arbitrary n and compute as n goes to infinity. So I'm going to first of all write down what the answer is, and then I'm going to show you where that comes from. So here is the basic answer. The basic answer is this result, that tau scales in the following way as n goes to infinity, goes as some constant. Let's call it actually. Well, I don't care about this constant. Let me just give it some dimensions. So some microscopic time scale times e to the some constant c times n to the power d minus 1 over d. So here, so tau naught, c are constants. Tau is a time constant, a microscopic time constant. C is some number. So I'm just going to say that these are order 1 as I take the limit n goes to infinity. That just simply says they don't depend strongly on n. And so what this says is the implication, if this is true, as n goes to infinity, the system gets trapped in the in one of the regions of phase space, and and the experimental implication is that we're not just talking, we can't obviously take the limit n goes to infinity in an experiment, but we can say that if the time that you're observing the system is much less than the ergodicity time, tau ergodicity, then you'll see ergodicity breaking. And in particular, you'll think of this as spontaneous symmetry breaking. So you'll see order and emergence. Okay, so that's the claim. And if it's true, this is how it justifies the idea that we have spontaneous symmetry breaking. So this trapping is called ergodicity breaking. And we've used the fact that there's symmetry here because we've divided the phase space up into ergodic regions, which are designated by the symmetry of the Hamiltonian itself. So let's just say that as a comment, the ergodic regions in phase space are related by the underlying symmetry of the Hamiltonian. And so that is the picture. I'll just make a side comment for some of you. So some of you may have heard of the term replica symmetry breaking. And you all know that Giorgio Parisi won the Nobel Prize for his work on this, replica symmetry breaking. So I'm not going to go into what that is. It's what does it really mean? Well, this is something that occurs in, for example, disordered systems, where there is quench disorder. What quench disorder simply means is that there are variables that are not in equilibrium. For example, crosslinks in a piece of rubber. So they are simply hard chemical constraints. And so that means that the polymers are limited by those constraints and can't move around freely as they would if they were in solution. They could be interactions due to impurity atoms in a magnet. And so that's another way that one can generate these things. And that, in fact, was the context in which Parisi did his work. So anyway, there's a lot of terminology there, but the remark that I want to make is that what replica symmetry breaking really means is that you can have ergodic regions, ergodic regions and broken ergodicity. Um, um, which are not related by symmetry. And I say a bit more about that in chapter 2 of my book, but I'm not going to say any more about that here. Okay, so now let's now try to see if we can understand how ergodicity breaking can work. So here is our strategy. So what we're going to do is we're going to, first of all, consider the case when uh, H is non-zero. So we're going to say I apply an external magnetic field to the system, and now that will orient the spins. If I was at absolute zero, it would orient all of them. If I'm not at absolute zero, there's temperature and thermal fluctuations. I will orient some fraction of them, and we can compute what that is. And so that'll orient the spins, and then we can ask how does the so that's step one, and then step two is we're going to ask how does the system make a transition? Let's say this H is positive. Um, how does the system make a transition from m greater than zero to less than zero? And you might say, well, that's going to be very difficult. If I'm orienting the spins in the positive direction, why would it ever flip in the opposite direction? Well, it's possible because there's thermal fluctuations. We have a Boltzmann distribution. The system um, can in principle flip. That's a rare but allowed possibility. As I make the magnetic field smaller, it's going to become more and more likely for that flip to happen. On the other hand, as the system gets bigger and bigger, the circumstances necessary for all of the spins to then flip and have a negative magnetization, that becomes harder. So you've got these two competing tendencies. And then we're going to see that there are two competing tendencies as H goes to zero. Let's say from the positive side, it becomes easier and therefore quicker to make this transition. But as n goes to infinity, it becomes harder because you've got more spins to flip. And so we have this competition between these two tendencies, and we're going to try to compute that. Okay, so let's draw a cartoon picture of what it is that we're going to try to achieve. So here's our basic picture. So here is our system. We have some underlying lattice, like so. Then I have my spins on the lattice. So there's some are up, some are down, some are up, some are up, blah blah blah. And then I'm going to have an external magnetic field in the positive direction, like so. And what I um, what I expect is that the spins are all so that would be a general state of the system. Um, I'm going to say that at time, so this is a general state of the system. I'm going to say, though, what I'm going to do is this. I'm going to set it to be like this at a time equals zero, still have the external magnetic field in the positive direction. But now what I'm going to do let's draw in my lattice so you just remember that it's there. I'm going to start off with a system actually with all the spins pointing down, like that. And then what I expect is that because I have an external magnetic field, the system will eventually, at time equals infinity, is going to be pointing in the up direction. Or let's say most of the spins are going to be pointing in the up direction. I'm not going to go into that distinction. So this would be, I've got m is less than 0, but I've got a positive field, and that's obviously an unstable situation. And then here, m is greater than 0, h is greater than 0, and that's a stable situation. And so and that's going to happen at time t equals infinity. I go here, I end up like this. And so what we want to understand is how this actually happens. So this is going to require a little bit of a digression into the kinetics of phase transition. So what we're going to ask is what is the kinetics of the phase transition? And we're going to just discuss this at a very rudimentary level. So we're going to look at the kinetics of this phase transition. Okay, so let's draw let's again do some cartoon pictures. The way that this is going to happen is through nucleation. So what we're going to talk about then is the nucleation and growth of a thermodynamically preferred state in a background of an unstable or non-preferred state. So let's think about this. Let's think about let's think of an example which might be the liquid gas transition. So I'm going to use the language of that for a few minutes, but then we'll talk about what that means in the case of a spin system. So so um, so this one is very easy to visualize. Let's say the liquid gas transition. And you've seen this every day when you boil some water in a saucepan. You see your liquid, your water just sitting there, and as it warms up, you see little bubbles that form, and those bubbles rise to the surface and generate vapor, steam, and uh, and so what that tells you, what your experience is, that the system uh, undergoes this phase transition through a succession of spatially non-uniform states. So we know that in the case of a liquid gas transition, you have a little bubble. And so we can think of it like this. Why do you get bubbles? Well, here is your picture of the system. Like so this now is physical space, not phase space. And what I'm going to draw is a background unstable phase, something like that. Um, this will be the background unstable phase. And I'll say a bit more what I mean by that in a second. And then in the middle there, I'm going to draw a little bubble, a nucleation droplet. We'll assume that this nucleation bubble has radius r, like that. And so this is a little bubble of the stable phase. Okay, so that is the picture. Now, when I talked about the background being an unstable phase, I actually don't mean unstable. So I want to make sure that you understand that. So I'm now going to just indicate that here by writing it like this. So I'm going to sort of cross this out, and we're going to say that this is really not unstable, but a metastable state. And same over here. So I'm going to now use the term metastable as opposed to unstable. Now, what's the difference? Well, an unstable state is one that will instantly decay dynamically into a more stable state, but a metastable state is a local minimum of the free energy. So here is the difference. An unstable state is absolutely unstable, and after creation will immediately start to decay through various mechanisms, which I'm not going to go into today, will start to decay into the true um, global minimum of the energy of the system. So that's what an unstable state is. A metastable state uh, is a local minimum of the free energy, but will eventually decay into the true global minimum. And that true global minimum is what we mean by the stable state. So if I want to, which I will in a minute, pictorially show you what I mean by that. So let's draw this picture over here. Let's draw, I'm using the word free energy. It's a bit of a lie. Um, and I will later be more transparent with you about what we actually mean by this quantity. So I'm going to call this free energy, but I'm going to put it in quotation marks because it's not really that. And in this position here, I've drawn it as a one-dimensional line. Chemists call this the reaction coordinate. And I have no idea what that really means, but it's a good term that indicates a concept that is vague. You understand what it roughly means, but it's not quite well defined. At least we haven't well defined it yet, but later we will define it much more precisely. And then the picture is that this free energy surface, this free energy landscape, if you will, looks something like this. So you might say, well, this thing over here is the system being in its let's say its liquid state, and this might be the system in its gas state. And what is happening is, well, actually, I'd rather do it the other way around. I'll do it the other way around, just to avoid confusing myself. This would be the liquid state, which is stable. And what you can see here is that there is an energy difference or free energy difference. So this the free energy difference is, if you will, the binding energy or the free energy benefit you get by going from the gas state into the liquid state. So here you might be thinking about looking at the system, um, temperature less than the boiling temperature, for example. Okay, so um, so that's the energy benefit, the energy gain. We get a lower free energy, and we like having a lower free energy. On the other hand, there is a barrier here, and that free energy barrier is going to be something that the system has to hop over. So we'll call that free energy barrier delta F. And because that free energy barrier is going to depend on the size of the droplet, then it'll be a function of R. So I'm going to write it something like that. And so this is the thing that we are going to we're going to calculate exactly what it is. Okay, so this is our picture, and then what's going to happen, the kinetics of the phase transition is that the system is going to be sitting around here and having some thermal fluctuations, and eventually there'll be some thermal fluctuation that will kick it over this barrier, like so, and then once it's got over the barrier, then it will go down to the state of global minimum, like so. So these are meant to be thermal fluctuations that activate the barrier crossing. Okay, so that's our cartoon picture. So let's say a little bit more about it. We can actually do a specific calculation of what the system is going to do. So so let's go back to our picture over here, and the question that we're going to ask is for this particular configuration, the question that we want to know the answer to is what is the free energy of this snapshot of the system? So that's the question that we want to know the answer to. And so now we're going to answer this question about the free energy. So the so again in this picture here, the background phase. I want you to think of this background phase as being as being the gas phase in our example. And then this drop bubble of the stable phase, that will be the liquid phase. And so what we are actually doing in this experiment is we're looking for a supercooled gas in the liquid state. So we've taken a gas, we've supercooled it, we're below the boiling temperature. It will eventually turn into a liquid, but in the meantime, we've got particles bouncing around in the box, and they haven't yet formed a liquid state, even though we are below the temperature where in equilibrium the liquid will form. So what we have here is we have a bunch of gas particles bouncing around in the box. The temperature is less than the boiling temperature. So in equilibrium, as time goes to infinity, uh, they will enter the liquid state, which is the state of lowest free energy. So the question we're trying to understand is what is the free energy of a configuration of the snapshot? So where would that snapshot configuration arise in the first place? Well, what I want you to think about is that I've got my particles bouncing around in a box, and every now and then, because of the interactions, so I've got my particles bouncing around in a box, and then they're all flying around them like this, and then you might wait, let's say, uh, you might wait, say, 10 million years. And then what happens is somehow, just by some chance fluctuation, the particles, a whole bunch of particles, have formed a little droplet, and then the rest of the particles are just bouncing around inside the box like this. So there's our little droplet formed by some chance fluctuation. And you think, great, this droplet is going to eventually grow and expand and fill the whole box, and we'll have the gas to liquid transition. But no, what happens is then this thing then evaporates. So you think, damn, that's too bad. Why is it evaporated? Well, if you go to the picture on the left, what it means is that that's one of these fluctuations, say over here. This represents a droplet that was unsuccessful. So it evaporates, so unsuccessful. So then, no problem. We're doing equilibrium statistical mechanics, so we have infinite patience. So you wait another, I don't know, 10 to the 6 years. No, why do we make it more spectacular? 10 to the 8 years. And now, this time, what's happened is the system's found its way into a configuration where now I have a nice big droplet. Let's say the one that I've drawn over there, and then around that are all the other gas particles. And now this droplet then is big enough. This is a successful droplet, meaning it has got to the top of this free-energy barrier. So it's a very large-scale fluctuation, and then this droplet then will subsequently expand and will eventually will fill the box. And so at long times, then you'll end up with the system in the liquid state. So that's the sort of that's the cartoon. The cartoon picture. Okay, so now let's go and build up the free energy of the system. So um, let's compute what is the free energy difference that is uh, attributed to the system due to the presence of the droplet. So this is composed of two terms. So one of them is going to be minus 4/3 pi epsilon r cubed, and this term is the free energy benefit that you get from being in the stable phase. And then the second term that we're going to have is a positive term. I'm going to write it down. These are terms I've not yet talked about. And this term is the cost of making a domain wall, an interface, between the two phases, in this case, liquid gas. So what that means is that if there is such a cost, then that cost is proportional to the surface area, proportional to the surface area times the surface tension. And the surface tension is what I've called sigma. And that's a positive energy cost. It raises the energy of the system, and the system wants to get rid of boundaries. And so because this is a positive surface free energy, the system will eventually find its way to a state where there's no surface free energy. And there's only one phase, and that will be the uniform phase of the system. So 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 this is all fine, but we haven't done any dynamics. So now I'm going to make a result from non-equilibrium statistical mechanics. So the question is, and now we have to relate this to kinetics. And so I'm going to just say that if I look at non-equilibrium statistical mechanics, I mean, it's beyond the scope of the course to explain this. I can work out write down a stochastic differential equation for how these thermal fluctuations cause the system to fluctuate, and then I can work out the rate, and so the time spent for the reaction to occur is going to be tau, and that is proportional to e to the delta f of r star. I'll see what that is in a minute, over kt. So this is a result, and I want to just say a couple of comments about this result. So first thing is that what do I mean by this r star? So this r star is the critical droplet, and that critical droplet is the one that has corresponds to the maximum in my free energy graph. Let me just draw my free energy graph again. It's already got too complicated, so let's draw it again over here. So this is R. This is my free energy graph. We're going to draw delta F as a function of R. So it's going to look something like this. So, so this is delta F as a function of R. I haven't drawn this graph yet, but it's related to the one on the previous page. So we've talked about delta F of R is the energy benefit. So what does this really mean? So R star is this point over here, and we'll compute it in a second. And so our picture, in terms of our reaction coordinate, we talked about that as some mythical multidimensional thing, but once I've constrained the system to be a droplet with a radius r, we can think of that r as being our reaction coordinate. And so what is happening is that our system, our picture of fluctuations is something like this. So the system is continually making little fluctuations, little experiments dynamically, making little droplets. Those droplets evaporate, then they start again, and so on. So those are the thermal fluctuations. And eventually the system, by luck, somehow manages to make a large fluctuation to this point. And then what's so great about this point is that now, if I now make a fluctuation in this way, every fluctuation lowers the free energy. Well, it's not really every fluctuation, because it is certainly true that I could have a fluctuation back into the metastable region, the gas region. That absolutely does happen. But let's now just think about what is essentially called the overdamped limit. And so once the system has got to the top, it will have have some probability of going down the other side. And so what will happen is it'll go down like this, go down like this, and so R will go to infinity. So what the picture is then is that the rate determining step for this reaction the rate determining step for the kinetical gas reaction is the formation of this critical droplet. And so it's not really the time for the reaction to go to completion. It's just the time that time is so much longer than the time going downhill. So this part of the process we can think of as being fast, and this part over here as being slow. And so we can think of this as being essentially the time for the reaction to occur, the time for the phase transition to occur. Okay, so that's our picture. So let's now compute what delta F star is. So d by dr of delta F of r should equal at r star should equal 0. And so that means if I just do the differentiation, then I get 8 pi sigma r star is equal to 4 pi epsilon r star squared. And so that tells me then that r star is equal to 2 sigma over epsilon. So that's our result for our critical droplet. Okay, so that's R star, and then I can go ahead and compute what the free energy barrier is for delta F of R star. So I just plug that in, and what I get is 16 over 3 pi sigma cubed over epsilon squared. So that's the free energy difference. So what we've got now is we're nearly close to the answer to our problem. So we know that the metastable state in our case, it's not a gas liquid state. The metastable state is the state with all the spins pointing down, and the stable state is all the spins, or the majority of the spins pointing up, and that's because we have a positive external magnetic field pointing in the up direction. So what we actually want, we want to know what happens as H goes to 0, because we're interested in the spontaneous transition. And so what that means is that as H goes to 0, well, the binding energy, the energy benefit is proportional to H. Epsilon is proportional to H. The stronger is the orienting magnetic field, the stronger is the bigger is the energy benefit you gain by pointing in the direction of the magnetic field. So similarly, as I take H goes to 0, epsilon goes to 0, and that tells me that R star goes to infinity. But R star can't go to infinity because we're in a finite box. With n less than infinity spins. And so what that means is that R star will saturate at the box size. Well, what is that box size? Well, we've got n spins in a d-dimensional box. And when I say box here, what I mean is the lattice. So I've got my system looking like this. Let's draw it in d dimensions. I can only draw in 3, so we have something like this. So inside the box, I have n spins. And I'm not going to try to draw the lattice. So what that means is that if I were to look at the dimensions of the box, each of these dimensions, these dimensions have size L, and that L is then proportional to n to the power 1 over d. Okay, because n cubed is the volume of the box in d dimensions. So I've got n spins in a volume v. The volume v is L cubed, and so L goes like n to the power 1 over d. Okay, so L is proportional to n to the 1 over d. So then, if I then compute what happens then, so what we've just argued is then that in the limit as h goes to 0, R star goes to some number of order 1 times n to the power 1 over d. And so then if I then compute what is delta f when epsilon goes to 0, so that's going to be 4 pi sigma times n. Well, in 3 dimensions, it would be 4 pi sigma times n to the 1 over d, which in this case is 3. Let's set d equals to 3 for now. So that would be n to the power 2/3. Just reading off delta f. And so this would be for and in general this would be some number of order one, something to do with the gamma function, in fact. So some order one number, which is just this 4 pi factor, times some sigma, and then this would be n to the power d minus 1 over d. And so that means that then the time, the ergodicity time, the time to go from metastable to stable in the limit as h goes to 0 is going to go like tau. It's going to go like some how do I write the result before? Some tau naught e to the c n to the d minus 1 over d, just as we had before, or just as I told you it would be. And so then as n goes to infinity, then I'm going to get ergodicity breaking. The system will never make that transition. And so it gets trapped in that region of phase space. Okay, so now we've talked about ergodicity breaking, and I'd like to talk a little bit about the mean field theory for the Ising model, and we'll finish this next lecture, but we can make a start on it today. So now we're going to talk about a simple version of mean field theory, which I'll always write as MFT, mean field theory of the Ising model. Okay, so what is our goal in this section? So our goal in this section is we want to compute the critical behavior. I'm going to show you how to perform mean field theory, what we mean by that. I'm not going to do it in a fully systematic way. I'll give you some ideas about that in the homework. We want to compute critical exponents. Scaling functions. And what we're going to see is that we get this is very successful. We recapitulate with a very small amount of work. What we see experimentally. So people always say, well, mean field theory is not much good, but it's a tremendous guide to the phenomenon, and is always the first thing that one tries in trying to understand emergence. And can it be improved? Yes, it can be improved, but to do that requires a lot of work, and so we need a renormalization group. Okay, so let's start off with a Hamiltonian. So H is minus J, average over nearest neighbors, I not equal to J, SISJ minus H, I equals 1 to N psi, so this is I equals 1 to N, and I not equal to J, so that's our system. The spins have the value plus or -1. And the partition function, the thing that we're trying to compute, is just trace of e to the minus beta h, which, as you know, in this particular case, means sum over all the degrees of freedom. So all of the SIs equal plus or -1, e to the minus beta h. And let me just write this out just to make sure there's no lingering confusion. This means S1 is plus or -1, S2 is plus or -1, so on and so forth, all the way up to Sn is plus or -1 times e to the minus beta h. And in some situations, one can solve this exactly. In one dimension is an example. But for now, let's just talk about why this is hard. And it's hard because of the interaction term, spin-spin interactions. So the spins are interactions, the interaction spins. Means that the partition function does not factorize. So all the cases that you know that you've done in statistical mechanics, such as the ideal gas, the paramagnet, and we'll go through the paramagnetic in just a second. All of those things can be done because the partition function, this thing we've written out here, it can be made to factorize, and you can see that the sums on the outside, these sums here. These are obviously factorizing. This part is factorizing, right? This is just a product of these independent sums, but this part does not factorize. And so that's why it's difficult. So the whole struggle in statistical mechanics is how to beat this thing into a form that is accurate and can be computed by factorization. So let's see how one might do that. We're not going to get super far today, but we will continue this next time. So how do we do this? Our strategy is find an effective spin model that can be factorized and includes the interactions. And and that's what we want to do. And the step that allows us to do that is if we can represent the spin interaction term, spin interaction. I'm going to write it like that: spin interaction as an interaction between spins and some effective external field, well, let's say spatially uniform field, then we can solve that exactly. So let's do this. Let's first of all set the interactions equal to 0, and let's see how we would calculate. So step 1 is we're going to ignore the interactions, And then that means that the spins are independent. So if the spins are independent, then I can write down that the partition function as a function of j and h. I've set j equal to 0. So now this is then just the following. It's the sum over all the si's equal plus or minus 1 times e to the minus beta h, but h is now has the j term cancelled, so it's just beta times h times the sum over I equals 1 to n of si. So that's what the thing looks like. And now you realize that I've got the sum of exponentials, the sum of terms in an exponential. Now this thing factorizes, and this thing factorizes. So let's go ahead and continue the calculation. So this then is equal to the product from I equals 1 to n. And I'm going to make the product of the sum over one of the si's of e to the beta h si. And this si can have the values plus or minus 1. And so there's two terms in that square bracket. And so this is then just the product from I equals 1 to n of e to the h si beta plus e to the minus beta h si. Like so, I've done the sum, and there's no si there, so that's completely wrong. So let me just take that out. Okay, corrected that mistake. So we've s is plus 1 gives you e to the beta h, s is minus 1, e to the minus beta h. So you get those two terms, and so this then is equal. This now is independent of n. Well, independent of n. It's independent of I. That's more what I really wanted to say. And so then this then is just 2 cosh of beta h. And then how many of these terms are there? There's n of these. And so it's this thing raised to the nth power. And so that's the exact result for the system without any spin interactions. And this describes what's known as a paramagnet. It's the spin equivalent of an ideal gas. It has no interactions. It just has the interactions with an external field. And so that's the result. And so now that we know the partition function, then we can compute the free energy. So the free energy is minus kBt times the logarithm of z, and so that is well, you can do that, and then you can compute the magnetization. So that's 1 over n sum over I si, and we know on general grounds, we talked about that last time, that is just df by dh. And so that means that this is minus, this is kBt over n d by dh of the logarithm of z, and log of z is the logarithm of the cosh. So when I differentiate that, what I get then is 1 over cosh times the derivative with respect to h of cosh, which is shine. And so in the end, I get that m is equal to 10th of H over KT. And so that is the that is the magnetization for a paramagnet. And there's no spontaneous symmetry breaking there. If there's no external magnetic field, if H is equal to 0, then M is equal to 0, just as it should be. Okay, so now the basic idea is step 2, an effective field, or a mean field approximation. And the idea is that when you switch on interactions, the interactions create at any given spin an effective external magnetic field. So let's see how that works. So here is the trick. So the trick is I'm going to write the Hamiltonian as minus I equals 1 to n of Si times Hi. So I'm going to write this. I'm going to try to find some effective Hi. That's an effective site dependent field, depends on I. And we can see exactly what it is because if I look at the original Hamiltonian, if you look at the original Hamiltonian over here, you can see that there's two terms. There's one external term, which is the external field over here on the left. And then you have the interactions, the first term. So I can just read off that this effective field is just Hi is equal to the external field plus the sum over J being a neighbor of I, J times Sj. And how many neighbors are there? Well, there are little z, which is coordination number, not partition function, coordination number of neighbors. So this if all the spins were pointing in the same direction, this would be little z times j. But let's just leave it like this, and I'm going to write this in a slightly more general way. I can think of this as h plus some sum over j of j ij sj, like so, and I think of jij is equal to 0 if I and j are not neighbors. And it's equal to j if they are. And oh, why is my screen freezing? 45, 46, 47. This is 48. Nope, it's not. It's 49. Ugh. Okay. This is 49. Let's try again. There we go, 49. And so then what I'm going to do is simply write that HI is equal to H plus the sum over this Jij, Sj, or the average of Sj, plus the sum over J of Jij times Sj minus the average of Sj. Okay, so this is the trick. This is the big trick. Okay, so this trick, what I've done here is this is a mean field because Sj is equal to a uniform average value. Independent of J, independent of the particular spin. So that's going to be a number that doesn't depend on position. This thing over here is the fluctuation about the mean. So 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 this is the fluctuation term, and the way we do mean field theory is going to be the mean field approximation is a very drastic one. It just says throw away the fluctuation term. So let me just quickly scoot through how this gives us a result. So the rest of it is quite straightforward. So let's see what happens. So if I ignore the fluctuation term, then this expectation value of S, this is in fact expectation value of this particular spin. This is just what we mean by the magnetization per spin, that is M. And so we have then that H I is equal to an effective H, which is independent of space, which is independent of coordinate, and that is just H plus 2D. This is the coordination number on the hypercubic lattice. Of a d-dimensional hypercubic lattice times J, the coupling constant, and then times M. Okay, so that's the effective Hamiltonian. That's the effective external field, and as promised, it is independent of I. So what that means is that our Hamiltonian of the system is now back to the paramagnetic form. The Hamiltonian of the interacting system is equal to the Hamiltonian of the paramagnet, but with an effective external field, H effective. Okay, so why is this great? This is great because now I can just solve the mathematics exactly and just plug into the formula on the left for the magnetization. So therefore, I can just read off that M is 10th of H plus 2D Jm over KBT. And this is where we're going to stop today's lecture. This is our final result. So what this tells us is that if I want to know what the magnetization is of this interacting magnet, what it actually is this self-consistent, nonlinear transcendental equation uh, that we have to uh, that we have to solve. And in next lecture, we are going to learn how to solve this um, using solve this graphically. So that's where we'll leave it today. And we went over a little bit over long because I was talking quite slowly for a change. And so next time we will finish the solution of the mean field Ising model.